Okay, hey everybody, we're going to go ahead and jump right into a new topic, complex numbers. So here's how it goes. Complex numbers are a really interesting topic. So we'll start out with this. And let's just take a look at some equations that we know how to solve. X squared equals 4. Okay, in order to solve that, we'll take a square root of both sides. So x will be equal to the square root plus or minus the square root of 4. Well, that's plus or minus 2. All right. This one here, we'll have to divide both sides by 3. And we'll have x squared equals 9. Well, that's just x is equal to plus or minus the square root of 9, which is 3. Okay, that's some pretty basic how to solve an equation with x squared equal to something. Okay, but now let's look at a question here. How about this? Okay, up until this point in algebra, we've learned that x squared, this has no solution. I can't find a number where when I square it I get a negative number. Okay, that's not entirely true. Now, we can't find a real number, okay? A number, and the real number, it's not a colloquial term, it's an actual term. There's a set of numbers called the real numbers, and amongst those numbers, this has no solution. But now we're going to add in a new number that is not a real number. This new number is called the imaginary number, and we denote it by the letter I, lowercase I. And we define this new number as the square root of negative 1. Okay, so we're creating a new number. It's called I, sometimes known as the imaginary number, and it is defined as the square root of negative 1. All right, so the square root of negative 1, first of all, again, is I. That's the definition. Okay, let's take a look at some problems we know. This number here can be written as the square root of negative 1 times the square root of 4. Okay, well, the square root of negative 1 is I, and the square root of 4 is 2. So this number, square root of negative 4, can be written as 2I. Let's take a look at this one. We can take the I out again. This is the square root of negative 1 times the square root of 9. So this can be written as I times 3, or 3I. Again, the square root of negative 8. Well, this can be written as negative 1 times 8. So the square root of negative 1 times the square root of 8, which is I. Now the square root of 8 is not a perfect square, so I have to do a little bit more simplification. This is 4 times 2. But 4 is a perfect square, so this is going to be 2I root 2. And the square root of 20, we can write this as negative 1 times 4 times 5. Now, the square root of negative 1 is I. Square root of 4 is 2. And the square root of 5 is nothing nice. It's nothing pretty, so we leave it as root 5. So the upshot here is we take I out of the equation, then simplify the square root as normal. Okay, let's look at some properties of I. This is pretty neat. So since I, I'm going to rewrite it up here, is defined as the square root of negative 1, if I square that number, I get negative 1. It's the number that when I square it, I get negative 1. Now, negative 1 times I again. So this is I squared times I. Okay, I to the cube is I squared times I. But I squared is negative 1. So this is equal to negative 1 times I, or simply negative I. So I cubed is negative I. Let's try I to the fourth. I to the fourth is I cubed times I. But wait, I cubed is the same as negative I. And I still have this I here. So this is negative I squared. But wait a minute. I squared is negative 1. So this is negative 1. This negative is right here. So negative 1 is 1. Okay. So I to the fourth is equal to 1. I to the fifth is equal to I to the fourth times another copy of I. But remember, I to the fourth is equal to 1. So this is equal to 1 times I, which is equal to I. Right? Weird, huh? I squared is negative 1. I cubed is negative I to the fourth is 1, and I to the fifth is I again. Well, that would mean that I to the sixth would be negative 1, I to the seventh would be negative I to the eighth would be 1, and so on. Okay, so I has some pretty weird properties. You keep on squaring it and multiplying it by itself again and again and again, and you get some pretty weird stuff. It's pretty neat. Okay, let's keep on going. All right, good. So now we need to define what a complex number is. Now, we often don't use the term imaginary number. I is the imaginary number, but we talk about not the set of imaginary numbers, but the set of complex numbers. So a complex number is a number that has both a real part and a complex part, or an imaginary part. So what I do is I take a number plus a number times I. Okay, so here's the part that is real, and here's the part that is imaginary. Okay, so every complex number has two parts, a real part and an imaginary part. Now it's completely possible that there is no real part and A is 0. It's also possible there is no imaginary part and B is 0. That's totally possible, and that happens often. Okay, but an imaginary number, or pardon me, a complex number is a combination of a real number and an imaginary number. And let's remember again that I is equal to the square root of negative 1, or oftentimes a better way to define I is to say I squared equals negative 1. These are the same statements, just in different forms. So some complex numbers. 3 plus 2i. Okay. 1 minus I. Maybe 5i. Here, a is equal to 0, right? There is no real part to this number. Here's another number. 2. That's 2 plus 0i. Okay. How about square root of 6? Say negative square root of 6 plus 100i. That's another one. Each one of these are complex numbers. Now it's kind of weird because every complex number has a plus or a minus inside of it. That's okay. But this entire thing is called that whole complex number. It's not two numbers, it's one. This entire thing is a complex number. Okay? Alright, here's some basics of I. I behaves in the same way a variable does, except when you raise it to a power, it changes, it becomes something new. So we want to think about I as behaving just like a variable. If this were 2x plus 3x, this would become 5x. So 2i plus 3i is 5i. Okay? So the complex number 2i plus the complex number 3i is the complex number 5i. There's no real part to this number, and there's no real part to this number, so there ends up being no real part to this number. Okay, 9i minus 11i. Well, 9x minus 11x, well, that's negative 2 times I. Now we get into some interesting things. What if we multiply these two numbers together? Okay, well, this would be, we have 3 times 2 is 6. I times I is I squared. Good, 6i squared. But remember that when I raise I to a power, it changes. I squared is equal to negative 1, so this ends up being negative 6. 4i times 2i, well, that's going to be 8i squared. Well, 8, that's not just a number, but I squared, remember, is negative 1, so this ends up being negative 8. This one's interesting. This requires foiling. Okay, so firsts, outsides, negative 3i, insides, 4i, last is negative I squared. Okay, let's combine like terms, just like we would do if this were a polynomial. We have 12. Negative 3i plus 4i is going to be plus I minus I squared. But remember, I squared is equal to negative 1. So this is really 12 plus I minus negative 1. So 12 plus I plus 1 is 13 plus I. So if I multiply the number 3 plus I times the number 4 minus I get the number 13 plus I. And again, we'll FOIL here. 12, that's firsts, outside, inside, oh, last. Okay, we're going to have 12, this is equal to 12. 6i minus 2i is 4i. And negative I squared, well, I squared by itself is negative 1, so negative, ooh, that's a negative, minus 1. Put those in parentheses, that helps. So I have 12 plus 4i plus 1. That's, again, 13 plus 4i. So the number 6 minus I times the number 2 plus I is the number 13 plus 4i. Okay, so we need to think about, well, why in the world are we going to do this? Well, we're going to graph these numbers. Okay, now they're easy to graph actually. This number, and this is the complex plane, this is not the x and this is not the y. Instead, this is the real numbers and this is the imaginary numbers. So I'm going to, for 2 minus 4i, I go 1, 2, and then negative, how many i's? Negative 4 of them. 1, 2, 3, 4. There's the point. So this is the number 2 minus 4i. This is the number 1. Okay, go to the right 1, and I go up 3. 1, 2, 3. And here's the number negative 3. So the real part is negative 1, negative 2, negative 3, and the imaginary part is 2. Okay. It looks kind of like the point negative 3 comma 2. This looks kind of the point 1 comma 3. This looks kind of like the point 2 comma negative 4. Okay. We're almost done here. Now, just like regular numbers, real numbers have absolute values, so do complex numbers. So the absolute value of a complex number is defined this way. It's the distance formula, the distance from 0. And it's a nice, easy formula. So if I want to find the distance from 0, the absolute value of this complex number, I do this. So I'm going to take the real part squared plus the imaginary part squared without the I and square root it. So I'm going to take the square root of 2 squared plus 1 squared. We don't include the I in this. This is going to be the square root of 5. This one over here, it's going to be the square root of 1, that's the real part, plus 1, that's the imaginary part, squared root of 2. We're going to take 3 squared plus negative 2 squared. There's no I there. So I get the square root of 9 plus 4, which is the square root of 13. Remember, a negative, no matter what it is, squared is positive. And finally, the square root of 4 squared plus 1 squared, which is the square root of 5. We're doing good, okay? So the absolute value of 2 plus I is root 5. The absolute value of 1 plus I is root 2. The absolute value of 3 minus 2i is root 13. And the absolute value of 4 plus I is root 5. Great. So we're going to look at this in class tomorrow, but I'll give you guys a just kind of a setup. Generating functions. This is where you get those really cool fractals, if you've ever seen those. And the idea is we have a function, but the input could be an imaginary number. Okay? And the idea with this is we'll plug in z equals 0, and we'll get an output. The first output will be negative 1. Then we'll plug it in again. We'll plug the output will be negative I. Then we'll put in negative I into z and see what the output is. Then we'll take that, we'll put the output of that into z and see what the output is. And you keep on going with that. So these make really cool fractals, and we'll look at those later on. Okay? But that's all we got for today. Okay? It's a lot of material, and it's a very interesting new topic. So we'll have some more fun with it in class. Thanks, guys.